Hello, in this video, I'm going to talk about forward kinematics of closed chains. In our course Introduction to Robotics, we have looked at forward kinematics for open chains. Any kinematic chain that contains one or more loops is called a closed chain. Here, I'm going to discuss parallel mechanisms, which are basically one moving and one stationary platform which are connected by several legs, and these may be open or closed chains. As you can see, these images represent two platforms connected by legs. This figure on the left is an RUS platform, and the figure on the right is a PUU haptic interface. As you can see, the types of joints labeled on the diagrams. As an example, this is the Delta robot, and it's a 3-degree of freedom mechanism, and you can see its moving platform is always parallel to the fixed platform. This pink area is its workspace. Recalling chapter 4 from our course, we saw that forward kinematics is finding the position and orientation of a robot's end effector frame from its joint coordinates theta. In the product of exponentials convention, we found out the transformation matrix from base to end effector frame in zero configuration and the screw axis, and used this equation to calculate the forward kinematics. However, here, forward kinematics means finding the position and orientation of the moving platform when we are given coordinates for all the actuated joints. Due to this forward kinematics can have multiple solutions as opposed to with open chains. The inverse kinematics for open chains is then easier, unlike that of closed chains. The forward kinematics of closed chains is more complicated than the forward kinematics of open chains. This is because the joints in the closed chain can be either passive or active joints. As you can see in the figure, only joints that move to their full freedom are active joints. Also, the variables must satisfy loop closure equations constraints, which can be dependent or independent based on the configuration. We will now analyze some parallel mechanisms. This is an RPR robot. First, its 3 revolute joints are fixed, then its 3 legs are prismatic, then there are revolute joints in the moving platform. The body and space frame are assigned as shown. Here, the 3 prismatic joints are actuated, the 3 revolute joints are passive. We denote the 3 legs by S1, S2, and S3, and RSP the orientation of the body frame. The forward kinematics problem is to determine, for given values of S, the body frame's position and orientation. P is a vector from origin of the S frame to origin of the B frame. As seen in the diagram, AI are vectors from the space frame to the revolute joints of the fixed platform, BI are from the body frame to the revolute joints of the moving platform, and DI are vectors from the fixed platform revolute joints to the moving platform revolute joints. Having defined these vectors, we can make a closed loop equation. As we can see from drawing the vectors, P plus B1 minus A1 is actually D1. This is also true for the second and third loop as observed here. So, we can write a general closed loop equation now. DI is P plus BI minus AI. Now, we want to set AI as AIX, AIY, and same for P and D in the S frame coordinates, and BI as BIX, BIY in the B frame coordinates. Consequently, we have this relationship, recalling that RSB is a rotation matrix of TSB. Now we define phi as the angle from x in S to x in B, and since SI square is DIX square plus DIY square, we can substitute to obtain this following equation. For forward kinematics, we have to solve the equation for P and phi, which is obviously not straightforward. However, we can use these substitutions to make things a little easier, where T is tan phi over 2, and sine phi and cos phi are defined as shown. We can reduce the 3 equations to a polynomial equation in T of degree 6. So, this has 6 forward kinematic solutions, and they may not all be physically reliable, and singularities may arise. This is a singular configuration. because extending the legs from this symmetric configuration can cause the platform to rotate either clockwise or counterclockwise. We don't know that. Or it can even cause it to snap. These are two possible forward kinematic solutions for the 3RPR robot. Here, the prismatic extensions are identical. So here we have a MATLAB simulation of the 3RPR robot. After defining the visual tools, we define these options and we have an initial guess for the forward kinematics right here. And then we're using this constraint function and iterative algorithm to solve for the forward kinematics. The constraint function is as follows. Over here in the inputs, the x is our current guess and a starting point basically for the position orientation. A, 1, 2, 3 are the base joint positions, B, 1, 2, 3 are the platform joint positions in the body frame, and S, 1, 2, 3 are the leg lengths, just how we defined them earlier. R is the rotation matrix RSV, and these basically implement the closed loop equation we made, which is di is p plus bi minus ai. These constraint equations basically implement our equation si squared is dix squared plus diy squared. After using these to solve the forward kinematics, these are from the solution, and we can edit them to see different outputs. Here we're calculating the platform position in the space frame, and this is for visualizing and drawing the diagram. As we can see in this diagram, this is one orientation position, so one solution for the forward kinematics. Here phi is 100.84 degrees, x is almost 2, and y is 1.18. We can change x and y randomly to see the effect. Over here I've changed x and y, and we can see this reflected in the output. Changing phi, we can see the different configurations. So if it's at 0 degrees or 360 degrees, this is a singularity configuration, as we discussed in our slides. This is a singularity configuration because if we twist it, we don't know how it's going to be. And then 90 degrees is one of the solutions for forward kinematics, and negative 90 degrees also another solution. We also saw these pictures earlier. Now let's look at the Stewart Gulf platform. There's 12 passive spherical joints at the end of the arms and 6 active prismatic joints, as you can see them move. Following the convention of the 3RPR mechanism, we make the definitions P, AI, DI as expressed in the S frame, PI in the B frame, and RSP, the rotation matrix from S frame to B frame. The vectors are as defined in the diagram. So now we have 6 equations, which is di is p plus rbi minus ai. If si is the length of leg I, si squared is di transpose times di, and we can substitute the first equation into the second one to obtain this. For inverse kinematics, given rp, we can obtain si, but for forward kinematics, we need to solve numerically for p and r. 6 further constraints are then imposed by the equation r transpose times r equals to I. We will then have 12 equations with 12 unknowns. Here, this is a simulation of a Stewart Gulf platform. Here, we're just constructing the structure and defining the leg lengths. For forward kinematics, again, we have used an initial pose and a constraint function. This is our constraint function. This is basically the pose. This is a calculation for the rotation matrix. And over here, we're using t to transform basically the equation di is p plus r into bi. And over here, this calculates the error between the actual leg length and the desired length, which is basically implementing the constraint of si squared is dit into d. After calculation, here we have Basically, these are for visualizing and drawing the stored platform, and we can see this diagram right here. But as of right now, we don't really have anything interesting to show, so we can try changing the position and the orientation. Here we can see the moving platform has moved to a side and basically matches its coordinates. Generalizing our concepts, we will now consider mechanisms where the legs are general open chains. In this diagram, the platform are connected by 3 open chains. The configuration of the moving platform can be denoted as TSP. So the forward kinematics of the 3 chains, denoted as T1 theta, T2 phi, and T3 psi, the loop closure condition is TSP is T1 theta equals to T2 phi equals to T3 psi. We can also write these equations as T1 theta equals to T2 phi and T2 phi equals to T3 psi. Each of these equations consists of 12 equations. RTR equals to R reduces the 9 rotation component equations to a set of 3 independent equations. So, as of now, we have 24 constraint equations, 12 of which are independent, with n plus m plus p unknown variables, recalling that theta is numbered from m, phi is numbered from n, and psi is numbered from p, as shown in the diagram. So, we have n plus m plus p minus 12 degrees of freedom. For forward kinematics, given d for the joint variables, we can solve the 2 equations for the remaining joint variables. Forward kinematics of a leg can then be evaluated to get the forward kinematics of the chain. Obviously, this is not trivial and multiple solutions are likely. Now, let's look at a 3 RPR parallel planar mechanism. Here, the prismatic joints are actuated. We can define AI to be the vector from the fixed frame origin O to joint AI in the fixed frame coordinates, BI the vector from moving platform frame origin P to joint BI in moving platform frame coordinates. Just like we defined theta in forward kinematics in our course, let's define theta I1 and I3 revolute joint angles at AI and BI, and theta I2 as a prismatic joint values for each rod AI-BI. The rotation metric R theta can be defined as follows. DI0 can be a unit vector from AI to BI. Currently, theta I1 is 0, so DI is R theta I DI0. So the position of BI is given by this equation, theta I2 DI plus AI is RBI plus B. For the forward kinematics, we have to determine R and P given theta I2. We have one unknown in R and two unknowns in P. R and P can be found from these equations. Theta I2 is mag RBI plus P minus AI. Here we also need to take these 3 defined constraints into consideration, and this is how we're going to find DI. Now we'll let a variable WI denote RBI plus P equals to theta I2 DI plus AI. Since WI is known for all 3, we can write R is just the product of this matrix containing W and this matrix inverse of the matrix containing B, where P is WI minus RBI. Please note that these resources were used to make this video. Thank you for watching and have a great day.